A single teaspoon of black hole material weighs 6 billion tons. Not a typo. Not an exaggeration. 6 billion tons from 1 teaspoon. And that is actually one of the less insane things on this list. Fact number 1. Time literally stops at the event horizon. Einstein predicted it. NASA confirmed it. And it is so bizarre that even physicists have to take a breath when they say it out loud. When you approach the event horizon of a black hole, that point of no return, roughly defined as the boundary where escape velocity exceeds the speed of light, time, as measured by an outside observer, does not slow down gradually. It stops. Completely. An astronaut falling into the supermassive black hole at the center of the Milky Way, Sagittarius A star, which clocks in at 4 million solar masses, would appear to freeze at the edge from our perspective. Their image would hang there, dimming and redshifting for billions of years. But from the astronaut's own frame of reference? They cross the horizon in seconds with no dramatic sensation whatsoever. This is called gravitational time dilation, and it is not a sci-fi concept. GPS satellites have to correct for it every single day, or your navigation would drift by 11 kilometers per day. Black holes simply take that same effect and crank it to an absolute, mathematical zero. 2 clocks, same universe, experiencing time at completely different rates because of gravity. Physics is not broken here, but your intuition absolutely is. Visual note: animated infographic showing 2 clock dials side by side, one near a black hole event horizon showing hands frozen, one in open space ticking normally. Use a blue to red color gradient to show gravitational redshift. Fact number 2. The fastest spinning object ever measured is a black hole. In 2006, astronomers using NASA's Rossi X-ray Timing Explorer trained their instruments on a black hole system called GRS 1915+105, located roughly 36,000 light-years away from Earth. What they measured was jaw-dropping. This stellar mass black hole, about 14 times the mass of our Sun, is rotating at approximately 950 times per second. Not per minute. Per second. That is 950 full rotations every single second, which translates to a surface spin at the equator approaching roughly 1/3 the speed of light. To put that in human scale, if you stood on the equator of that black hole's ergosphere, the region outside the event horizon where spacetime itself is being dragged around, you would be moving at over 100,000 kilometers per second whether you wanted to or not. This phenomenon is called frame dragging, or the lens-thirring effect, and it means the black hole is physically pulling the fabric of spacetime into rotation around it like a mixer stirring batter. Any object near that region is not just orbiting, it is being carried by the rotation of space itself. There is nothing on Earth, nothing in human engineering, nothing in the observable universe that spins faster. Visual note: diagram of ergosphere and event horizon as 2 concentric glowing rings, with arrows showing the rotational drag of spacetime. Color-coded velocity gradient from yellow at outer edge to deep red near the event horizon. Fact number 3. A black hole can evaporate, and the smaller it is, the hotter it gets. In 1974, Stephen Hawking published a calculation that made the entire physics community go silent. He proved mathematically that black holes are not truly black. They emit radiation. Slowly. Imperceptibly slowly for large ones, but they emit it. Here is how it works. Quantum mechanics tells us that empty space is not empty. It is constantly bubbling with pairs of virtual particles that pop into existence and annihilate each other almost instantly. At the event horizon, one particle from a pair occasionally falls in while the other escapes as real radiation. The black hole loses a tiny, tiny sliver of mass to power that escaping particle. This is called Hawking radiation. Now here is where it gets genuinely mind-bending. The smaller the black hole, the higher its temperature. A black hole with the mass of our Sun would have a Hawking temperature of just 60 billionths of a Kelvin, effectively absolute zero. But a hypothetical primordial black hole with the mass of a mountain, compressed into a space smaller than a proton, would have a temperature hotter than the core of the Sun and would be evaporating in a spectacular final burst of gamma radiation. The universe's most destructive objects are also secretly, slowly dying, and nobody told you that in school. Visual note: Infographic showing a black hole size to temperature inverse relationship chart. Large black hole in dark blue labeled cold, shrinking through orange to a tiny brilliant white dot labeled millions of degrees. Particle pair diagram at event horizon as a clean academic illustration. Fact number 4. There is a black hole that contains the mass of 40 billion suns. For a long time, astronomers thought black holes were monstrous but had limits. Then they found TON 618. Located approximately 10.4 billion light-years away in the constellation Canes Venatici, TON 618 is an ultramassive black hole, and that is an actual scientific classification, not a dramatic adjective. Its mass is 66 billion times the mass of our Sun. Its event horizon, the boundary of no return, has a radius of approximately 1,300 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. So the event horizon of TON 618 is 1,300 times the Earth-Sun distance in radius. Our entire solar system, from the Sun all the way out to Pluto, could fit inside the event horizon of TON 618 with room to spare. If you replaced our Sun with TON 618 right now, the event horizon alone would engulf Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and extend several times further still. Every planet, every moon, every asteroid. Swallowed by a boundary you cannot see, touch, or detect, you would only know you had crossed it when the math told you escape was impossible. Visual note, scale comparison infographic, our solar system overlaid inside a circle representing TON 618's event horizon. Use a translucent purple circle engulfing a to-scale solar system diagram with labeled planetary orbits. Fact number 5. Black holes can produce jets moving at 99.9% the speed of light. You might think a black hole is purely a cosmic vacuum cleaner, a one-way door where everything disappears. But some black holes are doing the exact opposite in one direction. Certain actively feeding black holes, known as quasars and blazars, are launching jets of superheated plasma from their poles at velocities so extreme that calling them fast feels like an insult. The blazar Markarian 501, located about 460 million light-years away, produces jets moving at approximately 99.9% the speed of light. These jets extend for hundreds of thousands of light-years, longer than the entire diameter of most galaxies. The exact mechanism is still being debated by astrophysicists, but the leading model, called the Blandford's-Najek process published in 1977, suggests the rotating black hole's magnetic field lines get twisted by the spin, creating an electromagnetic slingshot that hurls material outward at near light speed. The most destructive object in the universe is simultaneously one of the most creative, sculpting the galaxies around it, triggering star formation light-years away, and firing energy beams so powerful that if one were aimed at Earth from 6,000 light-years away, it would strip our ozone layer completely. From just 6,000 light-years. In a galaxy of 100,000 light-years across. Visual note, academic diagram of a black hole with accretion disk shown as a flat glowing orange ring, with 2 vertical blue jets extending upward and downward. Annotate jet velocity percentage and length scale in light-years using clean label arrows. Fact number 6. The information paradox. Physics has 2 contradictory laws that cannot both be true. This is the one that has kept theoretical physicists in open academic warfare for over 50 years. And there is still no resolution. Here is the paradox. Quantum mechanics has a fundamental rule called unitarity: information is never destroyed. Ever. The total information content of the universe is conserved, always, no exceptions. General relativity has a different rule: anything that falls past the event horizon of a black hole is gone. Causally disconnected from our universe. And when the black hole eventually evaporates via Hawking radiation, that radiation is thermal, it carries no information about what fell in. So, quantum mechanics says information cannot be destroyed. General relativity says black holes destroy information. Both of these theories have been confirmed by experiment to extraordinary precision. And they cannot both be right. In 1997, Stephen Hawking and Kip Thorne made a formal scientific bet with John Preskill about whether information escapes. In 2004, Hawking conceded the bet. He changed his position and argued information does escape encoded in the Hawking radiation in some subtle quantum way not yet understood. Thorne refused to concede. The Betts Prize was a baseball encyclopedia. 2 Nobel-level scientists. A 50-year argument. A baseball encyclopedia. And the answer is still not known. Visual note, split-screen infographic, left panel showing quantum mechanics, information conserved with a padlock icon and equation, right panel showing general relativity, information lost with an arrow disappearing into a black circle. A large red VS between them. Clean academic style. Fact number 7, a black hole once tore a star apart in real time and we watched. On March 28, 2011, NASA's Swift telescope detected a burst of X-ray energy from a galaxy roughly 3.8 billion light-years away, in the constellation Draco. The event was catalogued as Swift J1644+57. What astronomers were watching, in real time, was a star roughly the size of our Sun wandering too close to a dormant supermassive black hole, and being stretched and shredded into a thin stream of plasma by tidal forces in an event scientists call a tidal disruption event, or TDE. The process took the star that had existed for billions of years and converted half its mass into an accretion disk. The other half was flung outward. The resulting flare was so bright that if our eyes could see X-rays, that single event 3.8 billion light-years away would have been briefly visible in our sky. The energy output during the peak was equivalent to roughly 100 billion times the luminosity of our Sun, sustained for weeks. Swift J1644+57 was also one of the first events where a relativistic jet was observed in real time during a TDE, pointing almost directly at Earth like a cosmic lighthouse. We watched a star die. In real time. From 3.8 billion light-years away. And nobody on Earth felt it. Visual note, sequential diagram infographic showing 4 stages of a tidal disruption event. 1. Star approaching. 2. Tidal forces stretching the star into a stream. 3. Accretion disk forming. 4. Relativistic jet firing. Use warm orange and red color palette for the star, deep black for the hole, blue for the jet. Fact number 8, if you fell into a black hole, you might not die instantly, you might see the entire future of the universe. Save the most mind-shattering for last. This is the one. Most people assume falling into a black hole means instant death, spaghettification, crushing tidal forces, the end. And for a stellar mass black hole, yes, absolutely, the tidal forces would shred you at the event horizon. But here is what the mathematics says about supermassive black holes like the ones at the centers of galaxies. For a sufficiently large black hole, tens of billions of solar masses, the tidal forces at the event horizon are actually survivable. The curvature of spacetime changes so gradually at that scale that you could cross the event horizon without any local physical sensation at all. You would not feel a line. You would not see a barrier. You would cross into the point of no return experiencing what feels like normal space. But here is what several theoretical models, including work from physicist Amos Ori at Technion, Israel Institute of Technology published in 2012.